Thank you, folks. Welcome back again. Mm. It is we were discussing the vaporizers, heaters, and the other thing which are in our machinery space. The vaporizer construction, where we have explained you the shell, head, tube plates, inlet chamber, U-tubes, etc. And now you have already told me the design, why the U-tube design is there, because we want it to be able to be elongated. But now in elongation, when it is heated, it is a very strange way of elongation. Here you see the tube are more or less precise U-tube. But when the liquid will enter, the liquid will enter from here, which will be minus 161 roughly. And when it will leave, it will be nearly plus 10, plus 50, plus 80, whatever temperature. So you can imagine this line will be trying to contract or go shorter, and this line is going to be expanding. So this is why we have got that kind of flexibility available within this chamber. This will be something like this, where you have got your upper tubes very hot, start of the tube little very low, and slowly and gradually. So this U-tube design allows it to expand or contract within the shell, where the steam is coming and going out. So this is the same method, and so we have explained about the vaporizer, use of vaporizer. We can also take the vapor from the shore, and put it inside the tank. Very simple. So now when we vaporize, we have a choice to vaporize and give individual tank and give it to shore, or we can vaporize from one end, then pass the remaining to the second, and of course you will have a fairly clear interface of vapor and gas, and of course we can push it outside from the last tank. Now while we are discussing the gassing up, the second process after the gassing up is the cooling down. That process is kind of hand in hand, where we will do the gassing up, we will do the cooling down, and of course we'll avoid the thermal shock. So once we are gassing up, we are slowly cooling it down as well. And but for cooling down, normally we use spray rinse. We diffuse. So I will tell you about the cooling down also. To avoid the thermal shock, we want to avoid the thermal stresses on the system, to shrink tank to an associated fitting and fixtures to accommodate minus 161 degree temperature. And of course we do not want any excessive pressure during loading and transporting, and the spraying of cargo liquid into a tank at a slow rate, evaporating and expansion. It is like, we will just spray the liquid. Why we are spraying, I'm going to explain you in a wee while. Cooling down rate depends on the tank design and the size of manufacturer recommendation. Mostly, as a rule of thumb, the cooling down should be reasonably uh, slow, because to avoid the thermal shock or thermal stresses. They say it is approximately 10 degrees centigrade per hour, every hour. So, but in some of the bullet tanks and that kind of tanks where you can do maybe 30-40 degree per hour. So it again depends on the construction of the tank. Inert gas cargo vapor mixture goes to shore or reliquefaction plant. Problem with non-condensable gases, constant condenser vent. Okay, so mind that inert gas, there are certain gases which are not. Okay, so this is what is happening inside this tank. You may have a spray nozzle which will spray the liquid. What is happening here? We are going to explain you that once the liquid goes out, liquid stream goes out, the one drop will multiply itself into dozens or hundreds or maybe thousands of droplets, and those tiny droplets have a surface area, and from where they absorb the heat. This is one of the spray headers of NO96. Can you see the liquid is coming here? This is the big nozzle. And can you see how many spray points are there? There are so many. So this header is virtually on the top of the tank. I think they have taken it out for some repairs and maintenance. And then this will diffuse the liquid inside the tank, and that liquid of course will convert to vapor, and that vapor will absorb the heat of within the tank. So rather than in a normal refrigerator we cool down the sides, so here we will cool down the environment in the middle, and that environment will cool down the sides. Okay, so after the big nozzle, which can handle about 100 cubic meter per hour at a pressure of about 3 bar. So why I'm telling you, please note it down that this is what pressure you will be giving when you are using the simulator in NO96. Then there is a small nozzle, and you can see the nozzles are placed at a higher distance, and then there is also a center nozzle. So again, this is what will be, if we do not want the cooling to be very fast, we can use just 30 cubic meter capacity small nozzle and cool down slowly and gently. We may be able to use both of them at one time if we want the cooling gradient to be very sharp. Okay, so what we are trying to achieve, engineers in the class, you may be able to understand this more better. Some of my deck friends, deckies, may not be able to understand it very well, but I'll explain you. The cool down is the process where, this is just we are showing it for the water. You have an ice, solid, -5 degree. You put a lamp underneath it, ice, and you change the temperature from -5 to 0 degree. For example, you have used the energy of say 10 megajoules or 10 joules to bring this 1 joule you are putting energy, and it will change 1 degree temperature. So that you can see. So we call it kind of a specific heat. 1 joule energy gone, 1 degree temperature change. Fair enough. I can see it happening. I put in 5 joules, 5 degree changed temperature. But now, when the ice is on ice form, but on a 0 degree temperature, I am putting in my heat energy, but nothing is happening. I mean, no temperature change is visible. All that energy is gone in the tank, in the substance or water or ice, but no change in temperature. This change in temperature I cannot see. That's why we call that heat which is absorbed latent heat. And we call it latent heat of fusion because it will fuse the ice and turn it into the liquid. So that there will be no visible change in temperature. And then once we have got at this stage, latent heat of fusion has happened, then the water, we will start building, heating it further. Uh, so we will keep on heating it, and there will be change in temperature. Say again, 1 joule of energy we put, and we have got 1 degree temperature change. So on till we again get to the point of 100 degree centigrade. And at that point, we are still putting the heat energy, nothing is happening. It means there is something happening, but it is not visible. It is latent. That latent thing is the heat of vaporization. Now my water is turning into steam. Okay? And there will be a point when it is still 100 degree, but it exists as a steam, not as the water. And from there, we keep on heating it further, and we will get supersaturated dry steam or etc. So this is a liquid saturation point. This is a dry saturation. So folks, this line here is the enthalpy line. Heat inlet or heat outlet. If we go that way, it is heat outlet. If we are going this way, it is heat. And that is the basis of our enthalpy diagram. So again, this is the same thing. So vice versa, when we are cooling down, we are going in the reverse process, where we are removing the heat and taking the heat out by different medium. So this is what is happening in the heat removal in cooling down process. Okay, we are bringing the temperature down. We are removing heat. For example, 380 kilojoules per kilogram. We have taken it from plus 25 to minus 151 or minus 161 degree, and then we further go down. Okay, so this is on the bottom level. It is enthalpy, and this is the temperature. Let's see further that because we can see the change in temperature, it is evident that is superheating. And here it is just the latent heat of vaporization. So we are using that latent heat of vaporization and the vaporization process to remove the heat. Okay, so this is how we will come to a point where we will remove the heat from the system. So what is enthalpy? You have heard me a couple of times. None of you have asked me the question. Enthalpy is a thermodynamic measure of the total heat content of a liquid or vapor at a given temperature, and it is expressed in energy per unit, kilojoules per 1 kilogram. Okay? From absolute zero. So therefore, for a liquid vapor mixture, it will be seen that this is the sum of enthalpy of the liquid plus the latent heat of vaporization. Are we happy? Are we clear on that? That this is what we are trying to do. I understand this is the fire alarm test we are going through. folks, we will have to stop the lecture because of the fire alarm testing. Can you just hold on? I will check. Do you have to go? No, no, just wait. Was it just that?
Yeah, it was part of it.
Yes.
Everyone is sitting down.
No one problem. Yes, we haven't to stop. So, folks, sorry for this interruption. We had a fire alarm testing. Um, enthalpy, you can see the enthalpy increases when heat energy is in, and enthalpy decreases when the heat energy is out. So, what we are doing in our refrigeration cycle, we are playing with the enthalpy. We are taking the heat in, we are taking the heat out. Understanding of these things are very important for all of us. So there is another terminology which is we called entropy. Entropy of a liquid gas system remains constant if no heat enters or leaves while it alters the volume, and does not work but increases and decreases should a small amount of heat enter or leave. Its value is determined by deriving the intrinsic energy of the material by its absolute temperature. The intrinsic energy is the product specific heat at a constant volume multiplied by the change in temperature. Entropy is expressed in heat content per mass unit temperature in the SI and kilojoules. It should be noted that the reversible process in which there is no heat rejection or absorption or the change in entropy to zero. So I will just, in a simple word, we change the state from solid to liquid, and of course liquid to the gas. This is a pressure enthalpy diagram. Now, earlier on we have seen the temperature and enthalpy diagram. Now we have got a pressure on one side and the temperature on one side. So what we are trying to, if you watch this thing, folks, very carefully, there are three different states. Liquid, all this area here is liquid. All this area here is gas. But in between these two states, there is a mixture of liquid and vapor. So we do this journey from liquid to vapor in our refrigeration cycle. So this is what we are trying to do when we are trying to spray in the tanks to cool down. Cool down time and drop in temperature from whatever plus temperature, we slowly and gradually cool down. In the beginning, we will see it will be very sharp fall in temperature, but slowly and gradually this will go on a very easy curve, and nearly at 161 degree it will be fairly being changed. So now, rather than using any refrigerant, we are using LNG for cooling down itself. LNG does have a properties of refrigerant. So the amount of LNG used for cool down is proportional to the surface to be cooled down, brought down to cubic meter MQ of tanker capacity. For example, we have got 40,000 cubic meter. We have got 12-hour duration LNG we want to consume or evaporate, I would say, not consume, or we want is about 450 cubic meter. 125,000 cubic meter, 12-hour duration, 700 cubic meters. So we need certain amount of liquid which we can, consume, which we can calculate. But we can also do when we are cooling down. We cool down one tank, we pass it to the second tank, we cool down the third tank, fourth tank, and then the hot vapor we can give. So now we are gradually cooling down. It is not necessary you just give it to one tank and whatever the temperature you can need to give it to shore. So indicative cool down duration or the atmosphere change in LNG cargo tanks is for about of 125,000 cubic meter. LNG carrier which we are giving you for your working is about gas transport about 48 hours. Third in MoS Rosenberg, the round spherical tank is about 1. Yes, because why it is more required for MoS Rosenberg as compared to gas transport? Can you tell me? Any idea? My naval architect friends, why it is taking more in MoS Rosenberg and less in gas transport or membrane tank?
Because of the construction.
Because of the construction. They have there you are cooling down a very thin layer of invar. Here the very thick metal. And of course it is sitting on an equatorial ring which is direct contact from. So cargo tank cooling down reduces temperature into all displays and also into the interbarrier spaces, causing pressure drop. So if this pressure drops in the hold space or interbarrier space, what is filled in the interbarrier space? Can you tell me?
There's a
nitrogen gas.
Nitrogen gas.
You have started the nitrogen.
Yes.
So this is what you are going to watch. When you are doing the cooling down, you will have to watch that your cooling process and it is contracting, then your tank annular space pressure will drop or interbarrier space pressure will drop and you will have to give further nitrogen to it. Pressure drop into interbarrier space or hold space should be compensated with nitrogen inert gas or in case of hold space of MoS Rosenberg dry air as appropriate. So whatever is there, you need to give the same thing to that space more, otherwise that will go into vacuum. During cooling down, moisture content or remaining inert gas could cause, sorry for any spelling mistake here, cause big problems, pumps, valves and other equipment could stuck up. Avoid excessive tank pressure. Do not let the tank build the pressure in it. Okay, so primary installation space management during LNG transport, this is the nitrogen flow rate in different stages. While you are loading, very high. Beginning of loading, slightly low. Loaded voyage, more or less steady, nothing changes. Unloading, goes down. Beginning of ballast voyage goes further down. Ballast voyages further, and then at the same time it starts again. So means nitrogen management in the interbarrier spaces or annular spaces is also very important. Okay. Now we are going to do the cooling down after the gassing up, because these two processes we are going to do one after another in the simulator exercises now after this lecture. is that we are going to vent, uh, sorry, we are going to take the liquid from shore and we are going to just spray it from the nozzle, spray nose. And then whatever the vapor is going to expand and it is going to increase the pressure. So we will suck the vapor and give it to ashore. But if the ashore, if my uh, pressure in the tanks are getting high because I'm generating too much vapor and shore is giving me back pressure for receiving my vapor, I may have to take it to my compressor and push it out with force. So cool down process, 20-degree inside, 20-degree outside. This is what you are getting in your next exercise. Your spray lines on these tanks, which you will get now, will be here. That will be a straight line going from forward to aft or aft to forward. This is the view from the stern of the tank. Okay, this is your port side, this is your starboard side, and these are the rails. Like the other one, which you will have a center rail, it is a straight line here, pipe here. So you will spray inside the tank. The cooling down process starts. Remember, 10 degrees per hour. You will slowly cool down, and what will happen? The volume here reduces, and the tank starts shrinking. Start inside. Once you have reached, so this is the photograph of the spray rails now. Can you see at the distance? This is more effective spray rails because it is from forward to aft, very long spray rails. These are at the distance, so
more effective than the submerged one.
Submerged one, there's no submerged one. I mean, there was a round one.
Round one.
Yeah, that is an NO96 or MoS Rosenberg, more or less. This is an, the membrane tank. So this is just an steel information. Mind that why we are not giving a very strong thermal shock, because the ship is made of different type of steel, grade A steel, in this one grade D steel, grade E steel, grade E steel. Of course, the owners cannot make it with the very high quality steel because the cost of the ship will be very high. So they use the steel type of steel wherever or whatever is required. And of course, almost all of them have got the different qualities of or different capabilities of absorbing the thermal shock. So what type of containment system? Carbon-rich steel becomes brittle at cryogenic temperature. They have no strength against cold temperature. So special material required, stainless steel about 304L or 316L are used. Aluminium with 9% or higher of nickel. So this is again some metal low temperature tolerance. Mild steel 0 degree, arctic steel minus 55 degree, aluminium very good. Easily we can do minus 163. Invar we can do minus 163, and other steel is minus. If we ever drop liquid on the deck, this is one of the accident when the LNG was spilled.
Ex-merchants.
I don't want to name any ship. Okay. For obvious reasons. I'm sorry. But we are in a learning process. We just want to know what happens. So luckily we do not have so many major incidents. But you can see this was the brittle crack, which appear later. Can you see these are brittle cracks on the deck? Can you see it? Huh? Interesting thing for you? Huh? Is it clear over there? And the what has happened? The liquid was drained from here while evaporating on the side, and it has very brutally brittled the steel over there. Although this is a better quality steel on the top, mm, which can so this can happen.
So
That's what, yeah.
recently there was an accident on an LNG. There have been two accidents, I think, this year. Yeah, so they were supposed to be the safest ship on the Earth.
Yes.
But there was some human error and
That is, the industry is expanding so fast, and the trained personnel or experienced personnel are not developing as fast as. This is my personal opinion. I could be wrong, but that is the whole. That is why this project, these kind of projects are there, and what we are trying to do is to give the information to the people that whatever method that um, this could happen to your ship. So if you are aware of it, uh, then you can protect your ship, isn't it? Do you agree with me? Yeah. So, folks, in order to avoid this normally, because manifold area is one of the area which is very, very uh, dangerous, where or which is a high risk area where the liquid can fall, hmm, or overflow or leak or whatever. So that area we always flow the water on it. We call it water curtain. On your simulator, don't forget to start the water curtain before you start taking the liquid. Okay? So if the water is there floating on top of the deck, uh, any spill which is going to happen will be floating on top of the water and going down to the water. Okay? And then this is what we have got: ESD, comms and cables, pre-transfer. Now we are doing the preparation for loading. We will do the emergency shutdown test. We will do the pre-transfer meeting, ship shore safety checklist, steam to main engine, stop burning gas, tank gauging, manifolds connected, then purge with nitrogen. We do hot ESD and water curtain on, cold arm lines, do the cold ESD, and then start loading. That will be our secondary stage when we'll talk about the loading. So, but of course, we are now going to take the liquid from the shore. So, of course, you need to know the ship shore safety checklist. Part A, we will fill it whenever we will come to that was just generalized part of the tankers. But for especially part B, part D is for bulk liquefied. IGF has make a very good. I have created the information on it. The companies who are doing the bunker operations of LNG, they are creating their own checklists under the IGF umbrella, SGMF, sorry, SGMF umbrella, and they are going to work on that. So this checklist which you are seeing at the moment is from extract from the ISGOT, International Safety Guide for Oil Tankers and Terminals. So this is the part D, which is the bulk liquefied gases, which include all of them. So we'll have to do the ship shore safety checklist and the other bits which we are going to do prior the loading operation rather than.
this is every loading. We check the
Yes.
safety valve.
We do the safety valve setting, HP alarm setting, remotely operated valve, reliquefaction equipment, gas detection systems, alarms and controls, and emergency shutdown. Emergency ESD test is one of the tests which we will do when we are alongside and prior doing any operation. There are two types of emergency shutdowns. One is the hot ESD, hmm, once we come alongside, and once our lines and arms are chest and arms are cooled, we do the cold ESD test before getting the liquid into the tank, and that is what we are going to do in the exercises today. Okay, so this is just the sequence of operation which we are going to do, because we are going to take the liquid from the shore and give the vapor to the shore for our cooling down process or gassing up process. So we'll anyway have to do the this thing, and we'll do it prior the loading. So I will stop here, folks, and now on we will do two different exercises for cooling, for gassing up the tanks and cooling down the tanks. Once our tanks are cooled down, we will come back, we'll do this short presentation on loading and loading procedures and loading safety, and then we will go this later in the loading phase. So thank you very much, folks. We'll have a 5 minutes comfort break where in the meantime, I will load the simulator exercise, and we will start the simulator exercise soon. Any questions? No?
Like
yeah.
the simulator.
Yeah.
Ballasting like yesterday, I'd done it on board.
Yeah.
So I was pretty comfortable. So now for this simulation, will we get a paper or something where we can?
No, I will be going through with you all the way.
Okay.
But so if you do not understand these things, I'm here. Okay. But you have the basic knowledge. We are not expecting you to be perfect in this exercise, and by no means. The main thing is to give you an experience on the simulator, so you don't damage your ship. The other main objective is you need to have the right concepts, which I think you have developed, right concepts. Yeah, you are opening a wrong valve. I will ask you, why you are opening this wrong valve? What is the rationale behind it? And there are so many ways to skin the cat. Similarly, we have different methods of doing things. On board your ship or on board your bunker barge, you will have a set of written procedures or the recommended procedures, which will be produced by the experts who are who has already worked on or the naval architects, the gas experts. So you will simply follow the procedures, and you will have no problem. But the major understanding, what we want to create here, is, do you understand the subject? We are doing something, why we are doing something, and then you experience it. If you make a mistake here, you will have an experience like yesterday. Few of our colleagues here, you have noticed that they started ballasting the forward tanks, which was not really desirable. But they have managed to start the pumps and all that. Yesterday, you yourself have done the shunting of the pumps, you have experienced, and you have controlled it. So that is the experience which you are getting here, and you are learning what is the rationale behind it. Okay? Did I answer your question?
Yes.
Okay. Thank you. Can we stop? Our virtual learner, thank you very much. We are getting a 5-minute break, and we are coming back again with the simulator exercise. Just minimize.